All right, welcome back for part two, going over chapter two, which is linear motion, motion in one direction from the textbook, College Physics. Okay, so first I want to acknowledge just a little strategy that I used. One of the nice things about having these on video is if you are getting to a point where you're like, oh, I'm tired and I'm having a tough time thinking, which I definitely was yesterday afternoon, you can hit pause and then come back to it when you're feeling a little bit fresher. So I've taken a little break. I'm ready to think again. So we were last on page number 41 of chapter 2. So now we're going to continue from there, part 2. All right, we were talking about acceleration, and we were trying to figure out when acceleration is positive and when acceleration is negative. So let's take a look at these diagrams. So I'm going to kind of zoom this in. Oops, wrong thing. There we go. All right, so I'm going to zoom in like this, and we're going to look at 4 different cases. So the first case is if the object is moving to the right. So right here, it's moving to the right, and moving to the right is positive velocity. So that would be positive velocity because it is moving to the right. The other case where it's moving to the right is this one over here, moving to the right. So that would also be to the right, and that would be positive velocity. Then there's some cases where it's moving to the left, and sorry, that's velocity in the horizontal x direction. So the other cases are when it's moving to the left. Moving to the left is going to be negative velocity. Over here, moving to the left is going to be negative velocity. And we need to know which direction it's moving because that's going to influence our acceleration sign, whether the acceleration is going to be positive or negative. All right, so then it's going to be speeding up. So speeding up is going to be increasing the speed. So if I'm moving positively and increasing the speed, that would mean acceleration is going to be positive. All right, positive, positive gives me a positive. The other case is if it is moving to the left, so it's a negative velocity and it's slowing down. Well, slowing down means it's going to be getting slower. That's going to be a negative change, right? So a negative negative also gives me a positive acceleration. My acceleration is positive because it's slowing down in the negative direction, and 2 negatives make a positive. So in this case, they show it with a little graph. Positive, positive makes a lot of sense. The graph goes positive, right? I'm speeding up in the positive direction. But I'm also, if I start fast in the negative direction, fast to the left, and then I slow down, I'm getting less fast to the left, which means my slope is also positive. So the and then remember, slope of velocity is acceleration. So that if we haven't written that down already, let's write that down. Slope of velocity equals acceleration. Our negative cases would be if I'm moving to the right and slowing down is going to be negative. Positive times a negative gives me a negative slope, negative acceleration. So that's going to be acceleration is going to be negative. And that's acceleration sub x, acceleration sub x. And then the other case where I'd be negative is if I'm going to the left and speeding up. So speeding up is going to be positive. So in the negative direction, if I'm getting faster, then it would be a negative slope as shown here. So that would be acceleration is, negative. Okay, so that's just how to find the sign of the acceleration. It requires a little bit of logical thinking, which is why I'm glad that I'm doing it fresh. All right, so let's do a little stop and think. An elevator is moving downward. It is slowing down as it approaches the ground floor. adapt the information from what we just learned to determine which of the following velocity graphs best represents the motion of the elevator. Think about your answer, pause. Okay, welcome back. Okay, so I'm going to talk through my logic here. The elevator is moving downwards. Downwards means that my velocity is negative, right? Because I'm going down, and that's the negative direction. It is slowing down. So slowing down is also going to be negative. So the slope of velocity is going to be down, or slowing down, getting closer to zero. Okay, so that means towards zero. All right, so I'm going to start with moving downwards to figure it out. Okay, so this way would be moving upwards, right? I'm going positive. If the velocity is positive, I would still, this would be moving upwards but slowing down. So I need one of these two. Now that one's out and that one's out because those are both positive velocities. So I need to start with a negative velocity. Negative velocity and then getting closer to zero would be this one. So I'm thinking it's going to be B. The other option would be a negative velocity and then getting more and more and more negative, but that's a greater magnitude negative. So that would be speeding up in the negative direction, which is bad for an elevator. If you're going down and speeding up a whole bunch, it might not stop. So, or it will stop, but very suddenly. Ruh-roh. So I think it would be B because I start with a large magnitude, so it's going fast, and then it gets to a smaller magnitude velocity. See the difference between 0 and the line is getting really small. And because that difference between 0 and the line is getting smaller at the end than at the beginning, this would be a faster velocity. This would be a slower velocity, or a slower speed, excuse me, as I approach the ground. Great. So I feel pretty good about that. Let's do another stop and think. This one, a particle moves with the velocity versus time graph shown here. At which labeled point is the magnitude of the acceleration the greatest? Pause and answer. Welcome back. Okay, so the magnitude of the acceleration I know is the slope of velocity. And I don't care whether it's positive slope or negative slope, because the magnitude means don't worry about positives and negatives. I'm not going to treat it like a vector, just like a scalar. So to find the greatest magnitude, I'm going to take the slope of each line. So A, I'm kind of like that. That's my best guess at A. B is pretty much flat. C is going to be like that. And D is going to be really, really gentle, something like that. Probably even more gentle like that. Okay, so which one has the greatest slope? Well, it's definitely not B. That one has a slope of 0. D has a very low slope. A and C both have kind of significant slopes, but it looks like C is definitely steeper. So the correct answer would be C, because it has the steepest slope. And it's okay that it's negative because it just asks about the magnitude. Awesome. All right, let's keep it going. And we're going to flip forwards a little bit. Ooh, nice. To page 42. All right, on page 42, we introduce the idea of acceleration, and that you can find acceleration by taking the change of velocity divided by the change of time. In this case, it's the change of velocity sub x, but you could do this also the same for the change of velocity sub y, just horizontal velocity versus vertical velocity. Obviously, if an object is falling, if it's in free fall, then I would use, instead of x, I would use the change of velocity sub y, because things fall vertically, not horizontally usually. trying to think of a case where something could fall horizontally, I guess on a ramp, but it's still falling vertically because of gravity. So this would be for free fall. So I know that the change of velocity divided by the change of time, and then I'm given some examples here where the acceleration is equal to the that, and then if I wanted to, I could break this out a little bit and say that I know that the change of velocity, acceleration, is going to be the change. Sorry, I don't actually need to do the change. I'm going to break that down and say that would be velocity sub x final minus velocity sub x initial. So it'd be my final velocity minus my initial velocity, the change in velocities, and that would be over the change of time. I could then manipulate that equation if I just want to solve for the final velocity. So let's say I'm only interested in that value. To get that by itself, I'm going to start by multiplying both sides by the change of time, by the change in time. That gives me a delta t equals v sub x final minus the horizontal initial velocity. And then to get this by itself, since again, this is what I'm solving for, I just need to add vxi to both sides. And I get, my final answer would be v sub x final equals v sub x initial plus acceleration times the change in time. All right, and that's acceleration in the x direction as well, right? All of these accelerations, the acceleration and the velocity have to be in the same plane, in the same direction, so that they match. So I could turn that into that equation. Now, if we double check on your on your handy dandy AP physics equation sheet, this AP equation sheet is going to start becoming really, really, really helpful. This is the piece of paper that they will give you during the AP exam, and it has all of the equations that they think you might need for the test. And then on the back side of it, it also has a whole bunch of units and unit conversions. So it can be kind of useful as a cheat sheet. And we're going to be using it constantly during this class. So if you ever are trying to solve a problem, I have taken tests before, physics tests, like my physics credentialing test to be able to teach physics, where I got in there and I was like, ooh, they're asking about this thing and I have never heard of it. Dirty little secret, I barely took physics in high school or college. I kind of taught it to myself when I was teaching it. So I got into the test and I was like, they're asking for circular motion or something, but they're listing something with what looks like a funny looking W. I don't know what that is. I don't know any equations for it. But the cool part is you can look on this cheat sheet and find some equations with funny looking W on it. And you can be like, oh, it looks like this equation is really, really similar to the linear velocity equation. I'm guessing funny looking W stands for circular velocity or rotational velocity instead of linear velocity. And then you can actually look down here and see it stands for angular speed. So that's speed at an angle or rotational. Cool. So this can be really, really helpful. And so we're going to start referencing it a lot. The first three equations that are on here are three linear motion equations. And I've taken a picture of them for you and put them down here on our set of notes. So if we take a look here, there you go. These are the three equations from your AP equation sheet for linear motion. You'll notice that we just solved for one of them. I solved for, over here, vxf in terms of vxi plus ax delta t. That's the same equation as right here, just with some slightly different subscripts. Instead of using x sub f, they've just made it v sub x. Instead of using initial, they've used 0, so at the beginning for 0 instead of initial, and then the ax, and they took out the change of time, right? You can know that there's a change of time there, even though it doesn't have the delta. Okay, so our textbook uses slightly different subscripts than the AP test does. Either one can work. I'm generally going to default when I'm solving to the ones that are on the AP test. Even though our textbook uses finals and initials, I'll probably use x sub 0 if I can. Okay, so the first equation solves for the velocity if I know the starting velocity and the acceleration and the time that I was accelerating for. So this is assuming a constant acceleration. The next equation right here is based off of taking a look at a graph, here you go, of the area under the velocity curve. So in order to find this next equation, I'm going to take a look at the shapes that make up this velocity versus time graph, because the next equation solves for the distance or the displacement x. So if I'm looking for x, x is the area under the velocity curve. Remember, the slope of the velocity curve is acceleration. So slope of velocity is equal to acceleration. Area under the velocity graph is equal to the displacement, which is how far the object has gone. All right, so if I take a look at that area, there are two shapes that are broken down here. There is a triangle under the graph, and then there's a rectangle further under the graph. The width of both of them is from here to here, and that's the change from initial time to final time, or the change of time. Then they both start a little ways in, that far in. And we're going to call that the initial distance that you're starting from. And then the triangle has a width of that much. That's like the base. The height of the triangle is the acceleration times the change of time. So how much increase here? That would be the rise, or a measure of the slope. So if you take those pieces together, you can come up with the equation x equals x sub 0 plus v sub x t plus 1/2 at squared. We've used a similar equation, distance equals 1/2 at squared, previously. You might have seen the equation written before as distance equals 1/2 at squared, but remember we're substituting in distance for x, and that's assuming we're starting from 0 and I have an initial velocity of 0. This just gives me the option to have non-initial velocities of 0, so I can start from a running start, and I don't have to start at the origin. I don't have to start at 0. All right, so then our next piece is what I could find my velocity, but what if I want to find my velocity without knowing the time? What if I don't know how long I've been doing something? Use these two equations with a little bit of tricky math to derive this equation. If you need an equation without time, but with distance, velocity, and acceleration. So if I don't know the time it was in the air, I can still solve for the final velocity using this guy. Okay, so now I've got 3 equations for linear motion. They all have different variables, velocity, acceleration, and time in the first one, distance, velocity, acceleration, and time in the second one, if I'm starting with an initial velocity, or if my acceleration is going to be a constant one and I need the distance, right? If I need the distance in there, or velocity, acceleration, and distance if I don't know the time, but I do know some of the others. So these three are going to be super duper helpful for you. And then we can just use our needs and givens process, draw some diagrams, and try to solve from there. So let's see how we're going to do some of that. All right. So if we scroll down, we get a little stop to think. For our stop to think, I've got a few equations that I could possibly use. And the question is, a cyclist is at rest at a traffic light. When the light turns green, he begins accelerating at 1.2 meters per second squared. So I'm going to start circling the things that I know. He is at rest initially. How many seconds after the light turns green does he reach his cruising speed of 6 meters per second? And then also, how many seconds? Okay, so how many seconds is our need? I need a time. I am given that he is initially at rest. That means the velocity sub x0 equals 0. I am given an acceleration. An acceleration is 1.2 meters per second squared. And I am given his final cruising speed. So that is v sub x equals 6 meters per second. All right, so I've got an acceleration. I've got v sub x, 0. I've got v sub x, and I need the time. Okay, so I could do a few different things here. I could draw a little diagram. So I could show, here's my bicyclist. Perfect. That does not look like a bicyclist, but it's okay. He starts at rest. Then he's going to accelerate forwards for an unknown time. So I've got v sub x0 equals 0. I know that his acceleration during that time is 1.2 meters per second squared. And I know that his velocity final equals 6 meters per second. So if that helps, that's also good. And I could draw it slowly, bigger, 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 bigger. That's his velocity increasing as he's moving forwards. So you could draw it in a whole bunch of different ways. It's often helpful to draw a diagram. Once you have that, I know that I now need an equation that has time in it. So I'm going to go back up and I'm going to find an equation that has time in it that also has acceleration and 2 velocities. So I need acceleration, boom, acceleration, velocity sub x, and I need the time. I think my first equation is going to be perfect there, that one, because that has all of the correct variables and none that I don't need. So why don't I try it? I'm going to do v sub x equals v sub x0 plus a sub x t. My v sub x is 6 meters per second equals my initial 0 plus a sub x, 1.2 meters per second squared, times the unknown time. All right, so the 0 takes care of itself. Don't need to worry about that bit. I divide both sides by 1.2 meters per second squared. 1.2 meters per second squared. 6 divided by 1.2. I am going to need a little calculator there. And I find that that would give me 5 seconds equals t. So would it make sense for the bicyclist to take 5 seconds to get himself going or herself going? Oh, it's himself, he. Yes, that makes logical sense to me. to get up to 6 meters per second, which is about 14, 15 miles an hour. Totally valid. All right, excellent. So I'm going to go with E, 5 seconds. Okay. Next topic is free fall. So if an object is free falling, an object dropped from rest, the velocity vectors point down and get longer. So any object in the air is within Earth's gravitational field. The velocity vectors are always going to go down, 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 down in bigger and bigger increments because of the acceleration due to gravity of 9.8 meters per second squared. You can graph this showing every second in the velocity is going to get 9.8 meters per second greater in magnitude, but because it's going down, remember we said down was in the negative direction, we're going to say the acceleration in the y direction, the vertical acceleration, is negative 9.8 meters per second squared. If the object is initially moving up, the velocity vectors are going up, but getting shorter. Same deal, the acceleration is still down. Because it's slowing down as it goes up, it's still accelerating downwards. The entire time up, it's accelerating down. The entire time down, it's accelerating down because it's always being pulled by gravity down. Okay, one note here. G is equal, so when I say I have a gravitational force of G on the Earth, that is equal to 9.8 meters per second squared. That's the positive version. The acceleration due to free fall, because it's downwards, the acceleration itself is going to be negative G, which is equal to negative 9.8 meters per second squared. So it's a very subtle difference, but we say that G is always a positive value. The gravitational pull acceleration is positive, but then the acceleration due to the free fall, because it's downwards, we've set up as positive, down as negative, has to be negative 9.8 meters per second squared. Okay. So that's really all we need there. And then we are ready to solve some practice problems. So remember, when solving practice problems, it can be really helpful to draw a diagram. It can be really helpful to find your needs and givens, and then use an equation and plug in your values. So let's go ahead and do that. There's a whole bunch of practice examples, each one showing different ways of doing that. For free fall though, if you're going up or down, your acceleration is still down. Your velocity can be up because I'm rising, but rising more slowly, acceleration still down. All right, so find the height of a leap. A springbok is an antelope found in southern Africa that gets its name